Hi students, I am Sheeba from Emmanuel Arasar JJ College of Engineering. Today we are learn about the topic fiber bend loss and dispersion. First, we can see what is fiber optic cable. A fiber optic cable is a light pipe. It is used to carry a light beam from one place to another. Next, the fiber bend loss. Fiber bend loss is the loss of optical power that happens when a fiber optic cable bends. When the bend is too sharp, the angle of the light changes. The light fails to reflect inside the core, escapes through the cladding, and radiates out as a signal loss. Optical fibers suffer radiation losses, which causes the light energy to be radiated from the fiber. Whenever an optical fiber undergoes a bends or curves on their path. Next, the types of bending loss. There are two types of bending loss. First one, macro bending. Second one, micro bending. Macro bending means a large visible curve or loop in the fiber. It happens when you wrap or pull a cable past its safe limit. These losses occur when the radius of curvature of a bend is greater than the fiber diameter. As the radius of curvature of the bend decreases, the loss increases. The bend radius is made smaller, it will reach the threshold point, then the losses become extremely large. Next is micro bending. Tiny microscopic twists or bumps along the fiber surface it occurs. It happens due to poor manufacturing or heavy pressure from an outer jacket. How to prevent it? First way, respect radius limits. Never bend or coil cables tighter than the minimum bend radius. Second one, use better cables. Choose bend insensitive fibers that hold light tightly in the core. Third one, avoid tight ties. Do not squeeze cables too hard with ship ties or clips during setup. Next one is macro bending loss. Macro bending loss is a loss of light signal strength. That is, it reduces the light signal strength. It happens when an optical fiber is curved or bent into a large loop or a tight radius. This bend changes the angle of the light. The light fails to reflect inside the core, escapes out through the cladding, and radiates away. The amount of optical radiation from a bent fiber is depending on the field strength at Xc and on the radius of curvature R. The macroscopic bending losses occurs. First one, angle change. The light hits the bend at an angle that is smaller than the critical angle needed for total internal reflection. In this case, the macroscopic losses occurs. Second one, speed limit. Light on the outer edge of a bend must travel faster than light on the inner edge to keep up. Third one, radiation. When the outer light needs to move faster than the speed of the light in that material, it breaks away lost radiation energy. Next is key factors. First one, bend radius. Smaller bend sizes cause more light to escape and increase signal loss. There is a specific shape limit. That means bends larger than this limit are fine, but bends tighter than this critical radius cause high loss. Longer light wavelengths, that is like 1550 nanometer, are more sensitive to bends and leak more easily than shorter wavelength. How to prevent the macroscopic bending losses? Do not wrap fiber cables tighter than the manufacturer's recommended minimum bend radius. Use bend insensitive fiber types for tight indoor harness or tight spaces. Route cables smoothly with wide, sweeping loops instead of sharp right angles. Next is micro bending losses. Micro bending losses in optical fibers are tiny, random shifts in the fiber axis caused by outside pressure or tight cabling. These small shifts force light to leak out of the fiber, which causes high signal loss. Microbends are due to small scale fluctuations in the radius of curvature of the fiber optics. This situation arises when the fibers are incorporated into cables. When microbending losses are occurs, the causes are side pressure from tight outer jackets or spooling, rough surfaces pressing against the glass core. Third one, temperature changes that make cable layers string or expand. Fourth one, bad manufacturing with uneven coating thickness. How it affects signals? First one, light jumps out of the main core path into the cladding. Second, signals get weaker over distance. That is, for more distance, the signals may be weaker. Third one, different light paths mix together and distort data. Next, we can see how we can stop the loss. First point, use strong dual layer polymer coatings to absorb physical shocks. Dual means double layer. Second one, design looser, softer buffer tubes inside the cable. Third one, choose bend resistant glass designs with higher numerical values. Next one, dispersion. Dispersion means the act of spreading things out or scattering them over a wide area. Depending on the subject, it has specific meanings in physics, statistics, and chemistry. It results in the introduction of inter-symbol interference. It also limits the information carrying capacity of fiber. Next, we can see the types of dispersion. The dispersion can be divided into two types: intramodal dispersion, intermodal dispersion. For intramodal dispersion, there are three types, that is material or chromatic dispersion, waveguide dispersion, group velocity dispersion, or modal dispersion. First one, we can see the chromatic dispersion. Chromatic dispersion in an optical fiber happens when different colors or wavelengths of light travel at different speeds. This speed difference stretches the light pulses as they move. When pulses stretch and overlap, the receiver cannot read the data correctly. This limits how fast and how far data can travel. The other name of chromatic dispersion is material dispersion. The chromatic dispersion exists due to the variation in index of diffraction as a function of an optical wavelength. Pulse broadening due to material dispersion results from the different group velocities of the various spectral components launched into the fiber from the optical source. The causes of chromatic dispersion. First one, material dispersion. The glass inside the core changes its refractive index based on the wavelength of light. Different wavelengths experience different amounts of slowing down. Second one, waveguide dispersion. Light travels partially in the core and partially in the cladding. The distribution of power changes with wavelength, altering the overall speed of the signal. The effects and solutions. First one, pulse broadening. Signal stretch over time, causing errors at high data speeds. Dispersion compensating fiber. Special fiber modules with opposite dispersion characteristics cancel out the distortion. Third one, fiber frag ratings. Reflective tools used in line to fix timing delays in specific wavelengths. Next one, material dispersion. Material dispersion is a form of chromatic dispersion where an optical pulse spreads out because the refractive index of the fiber core material changes when the wavelength of light. Because different colors or wavelengths travel at different speeds, signal components arrive at different times, limiting data rates. The key causes of material dispersion. First one, refractive index changes. The glass index changes depending on the light wavelength. Second one, different speeds. Each wavelength inside a light pulse travels at a unique group velocity. Third one, pulse broadening. Light spreads out over distance, causing adjacent data bits to overlap and create errors. The characteristics of dispersion. First one, zero dispersion wavelength. For silica glass fibers, material dispersion drops to zero near the 1300 nanometer wavelength region. Second one, units. Measured in units are of picoseconds per nanometer kilometer. Third one, source dependence. Affected directly by the spectral width of the optical source. Wider spectrums cause worse spreading. How to reduce material dispersion? First point, use light sources with narrow spectral width such as laser diodes instead of LEDs. Operate communication systems near 1300 nanometer where material dispersion is minimal. Employ dispersion compensating modules or specialized single mode fibers for long haul networks. Next one, waveguide dispersion. Waveguide dispersion is a type of chromatic dispersion caused by the physical geometry and dimensions of an optical fiber's core and cladding. Because different wavelengths travel partially in the core and partially in the cladding at different ratios, they move at varying group velocities, which spreads the light pulse over time. Waveguide dispersion occurs when a single mode fiber only confines about 80% in the optical power to the core. Dispersion arises from the 20% of the light propagating in the cladding, which travels faster than the light confined to the core. The amount of waveguide dispersion depends on the fiber design. The key causes of waveguide dispersion is first one, geometry dependent speed. The effective refractive index depends on the ratio of the core radius to the wavelength of light. Second one, power distribution. At longer wavelengths, more optical power travels in the cladding rather than the core, changing the overall speed of the signal. Third one, single mode impact. It is a major factor in single mode fibers where intermodal dispersion is absent. Next is the main characteristics of waveguide dispersion. The waveguide dispersion is a part of chromatic dispersion. It combines with material dispersion to form the total chromatic dispersion of the fiber. Second one, design control. Unlike material dispersion, engineers can tune and minimize waveguide dispersion by altering the core size, profile, and the refractive index difference. Pulse broadening causes signal distortion over long distances, limiting high data rate transmissions. Next one is intermodal dispersion. Intermodal dispersion or modal dispersion is a signal distortion process in multi-mode optical fibers where light rays travel at different angles and path through the core. Because different paths change the transit time, light packets spread out and blur data over distance. The causes of intermodal dispersion. First one, different path length. Rays traveling straight down the center take the shortest path. Rays punching at steep angles travel a longer zigzag path. The second one, varying speeds. Even though the material is the same, geometric path differences cause modes to arrive at different times. It only occurs when a fiber core is wide enough to support many light paths at once. Single mode fibers avoid this completely. The effects on fiber axis. First one, pulse broadening. It is input signals stretch out over time, causing adjacent bits to overlap the signals. Second one, lower bandwidth. The lower bandwidth limits how fast data can move. That is, for lower bandwidth, the data can be faster. Third one, short distance limits. It restricts multi-mode systems to shorter links unless corrected. Next one, how to reduce the dispersion. First one, graded index fiber. It changes the core's refractive index smoothly so outer path light speeds up, equalizing arrival times. Second one, single mode fiber. It uses a very thin core so only one direct light path exists. In this section we can conclude the topic. So thank you.